So the next talk is by Marcelo Sousa on abstract interpretation with unfoldings.
Okay, thank you. I'm Marcelo. I'll be talking about abstract interpretation with unfoldings. This is joint work with Cesar Rodriguez, Vijay Da Silva, and Daniel Kroning. The motivation for our work is automated verification of concurrent programs. In particular, our focus is safety. So, for example, if you are given this program, we want to prove that there is no execution of this program where the assertion is going to be violated. Now, let me just tell you this program is safe, but quickly just looking at it, it has two threads. Both threads start with a loop. They perform some computation over their local variables. Then they perform an access to a global variable k, and then finally thread 2 asserts that k is less or equal than 250. Now, in general, verifying concurrent programs is quite challenging, especially if you're trying to do it automatically. This is because of the state space explosion. And now what I want to show you is 3 sources of explosion that we focus on this work. And to do that, I'm going to use the same program as before. And on the right hand side of the slide, I'm going to show part of the state graph where I'm going to show these sources of explosion. So the first one that we can consider is data. So initially, we know that because I can have a non-deterministic value between 0 and 99, then our state space immediately starts branching with 100 possibilities. The second source of explosion that we consider is the usual one, meaning we have a combinatorial explosion because of concurrent actions interacting. And the third one is the fact that it is possible that at a particular control location we may have multiple branches enabled. So here we label that as a control non-determinism. Now I want to take a brief look at previous approaches for this problem. And the first one is dynamic partial order reductions. Now the idea here is to exploit the fact that certain concurrent actions are independent, and which allows us to explore a reduced execution tree. But if you look at the part of the state graph, you see that these approaches, they mostly focus on explosion because of concurrency. Now, these approaches have been extended with multiple combinations of other approaches, which I label here as symbolic PORs, and there is a large amount of work on this. But for example, if you take a prominent technique here, which combines symbolic execution with partial order reduction, where the idea is now to explore a reduced abstract computation tree, we are still going to face several problems. The first problem is that, which is shared by all these symbolic PORs, is how do we compute the independence relation now? And the second problem is that this approach will still have to cope with, will still not handle a path explosion. Now, more recently, we have seen that there are new approaches coming out. In particular, there is a combination of thread modular reasoning in the style of, for example, relay guarantee with abstract interpretation. So the focus of this approach is, the problem with this approach is not the scalability, but it's more of an imprecision. And why is that? That is because the approach has to compute for each control location of one thread what is the flow of information to other control locations of other threads. And because it typically over-approximates this information, it's losing precision. So what is the insight here? The insight is that, well, on one hand, we have PORs, and PORs fundamentally talk about or handle executions, so they are over execution trees. On another hand, we have abstract interpretation, which is computing fixed points over CFGs, typically. And so what we want to combine is the POR precision with the scalability of an abstract interpreter. So we called our approach Causality-Based Abstract Interpretation, and it's going to handle all these sources of explosion. So what do we get out of Causality-Based Abstract Interpretation? Well, first of all, we combine the advantages of a POR with an abstract interpreter. We are going to be precise for properties which are sensitive to history about multiple threads. Because we are using true concurrency semantics, in particular using Winskill's event structures, we are going to be able to naturally cope with non-acyclic state spaces. And these are particularly important because once we consider data abstractions, the state space is typically going to contain cycles. And finally, one of the key designs of our approach is that we want to be able to port an abstract interpreter for a sequential program into a concurrent program. And we want to be able to reuse current methods for computing independence with data abstractions. So the main challenges are how do we compute the independence relation, first of all, and second of all, how do we combine a POR with abstract interpretation. So let's go back to our running example, and now I want to show you 6 concepts, 6 transformations that explain our technique and explain the main features of it. So the first thing we need to do is we need to pick a data abstraction. Let's pick one of the most common ones, which is intervals. So essentially what the initial state for the variable y is going to now be the interval 0 to 99 instead of a set of values. But now the first thing we need to come up with is how do we compute an independence relation for intervals? So this essentially is, we had to research on how to do independence for transformers. Now our first result is that the standard independence relation does not work with transformers. So what do we mean by this? We mean that if we compute an independence relation in the normal sense of a POR over statements, once we consider the concrete semantics with sets of states, we cannot take that independence relation and lift it to the transformers. So this motivated us to come up with a new notion of independence, which will prove that does lift to transformers. And now I want to show you 2 phenomena which happen when we interact data abstractions with independence. The first one is abstraction creates independence. So let's take a look at an example. So we have two concurrent transformers. We have A and B. A is assume x is different than 9, and B is x plus plus. Now if you consider the sets of states for the variable x, and let's consider the initial set to be the values from 0 to 10. We immediately are able to understand that these 2 transformers will not commute. Now, let's consider what happens when we have an interval, 0 to 10. Now, we'll see that they do commute, and this is because the transformer A will not have any effect over that initial interval, nor the interval where after we apply B. So this is kind of nice because it basically implies that once we apply a data abstraction, we could actually perform a more aggressive reduction of the state space than we could before. But unfortunately, we also see the opposite scenario, which is abstraction can also break independence. So let's take a look at another example where now the transformer B is not x plus plus, but it's assume x is less than 10. We now have that in the concrete transformers, they will commute because they are just filters, and these filters will commute no matter what initial state you have, initial sets of states you have. But now if you have the same interval, 0 to 10, they will not commute anymore. And this is because after I apply the transformer B, I have the interval 0 to 9, and now the transformer A does have an effect on that interval, and this gives the interval 0 to 8, while on the other side we have the same, the interval 0 to 9. So now we have different results. So this was kind of bad news in the beginning for us because we didn't know how to really handle this. But in fact, we were able to show that it is sound to consider these transformers independent. And that is because they were independent in the concrete semantics. So this basically means that we can inherit, when we apply data abstraction, we can inherit the independence relation from the concrete semantics to the abstract semantics. So now I want to show you the data structure, the semantic object that our method actually reasons about, which is a prime event structure. And the concept of getting to a prime event structure is two-folded, which will lead us to steps 3 and 4. So the first step is, okay, now we have an independence relation. We are going from executions to partial orders. So the first thing we do is we compute, we get an abstract execution somehow. So here is one of them. And here I mean the transformers for the labels, not the actual statements. So you can see that this abstract execution is safe. It's obtained by first doing thread 1 and then doing thread 2. And now what we know from concurrency theory, in particular Mazurkiewicz trace theory, is that if we have an independence relation, we can transform this execution into a partial order, right? And the only thing to note is that, well, the accesses to the shared variable k are going to be totally ordered in the same order that we had for the abstract execution. Now, the elements of this partial order are going to be called events. And as we know, a partial order is going to potentially represent multiple executions. So the process will continue by taking other executions and getting other partial orders out of it. And the second conceptual step is step number 4, where we go from a set of partial orders to a prime event structure. So if you've never seen prime event structures, they are quite simple to understand. You take a set of partial orders, and you're going to compact represent them by sharing their prefixes, sharing common prefixes. So if we take the 2 partial orders that we had before, we start by representing the common parts of these partial orders. So that's the step up to doing an action on K. And now, when the structure starts diverging to represent branching, meaning to represent we are now representing multiple partial orders, we use the so-called conflict relation to represent that. So that's the dashed green relation between events. And this is the way that this structure is representing branching. And then the construction will continue until we represented the set of partial orders. So the 2 observations, the first observation is that this is a representation, meaning there is no abstraction happening from a set of partial orders to a prime event structure. And a second observation is, going back to the title, for the Batch.net community, this is what it's called the unfolding, the net unfolding. So a prime event structure is constructed via iterative insertion of partial orders until fixed point. But in the case of programs, we can actually have these executions might be infinite, so we may have infinite partial orders, so we may have, in theory, an infinite object. So we need to come up with a smart way of achieving termination. And this is our fixed point detection. So we have borrowed from the unfolding community the notion of cutoffs, and we have extended it with subsumption. So as an example, what can happen is, so say we are in the loop head of thread 1. So the only thing that matters from the state is the value of variable I, the interval for variable I. So we perform plus I. So we are now in 1 to 100. Then we are going inside the loop. So we apply the loop condition, which removes the element 100 out of it. And then when we go back to the loop head, we have this state here. So what we can observe is that per variable, the intervals are going to be subsumed, and we are in the same control location. So the advantages of the theory of cutoffs is that we are able to handle with non-cyclic state spaces. But furthermore, if we actually had a cyclic state space, we could actually accelerate the fixed point using cutoffs. And a perhaps downside is that we have to have some notion of state, either with a hash or with the actual state, because we need to perform this subsumption check. So our last step is called thread local merging. So currently, the analysis so far, as I explained to you, for the thread number 1, it would create this sort of branching structure, and that is because if after I do the event plus I, now I'm in the head of the loop, and now both branches might be enabled. So that's the first branching that is happening. So if I go inside the loop, then I have another non-deterministic conditional. So I have more branching and more branching. So this structure so far is branching a lot. So the idea is, okay, can we use an abstract interpreter to collapse all these conflicts which have nothing to do with concurrency? And it turns out that we can, and the concept is in fact quite simple to understand. So what we are going to do is we are going to replace a transformer replication, as we have in this part of the figure, with a controlled fixed point of the thread. So what sort of control fixed point of the thread are we going to do? We are going to do one that removes, that collapses all the local code of the thread. Okay, so in this example, the entire loop, instead of becoming with this branching structure, is going to become just one event, which represents running an abstract interpreter for a sequential programmer over this loop. So causality-based abstract interpretation is about, in some sense, about merging partial orders with similar local interference. So going back to our running example, here what we are going to do is we are going to take both of these loops and apply an abstract interpreter on them and get only 2 events, which compute the invariant. So the structure, the computation will continue, the construction of the unfolding will continue, and you see that out of an unfolding that was exploding, we get a very, very compact unfolding, which is still able to prove properties with respect to concurrency. So what I want to remark is that this approach is happening dynamically. Okay, so this is not a static pre-processing process where we identify what parts of the code are local. Okay, so we have implemented this technique into a tool called APoet. It has implemented an unfolding algorithm, which is a super optimal partial order reduction, in fact. And we have implemented together with an abstract interpreter with intervals. It's available on GitHub. So please talk to us, and if you want to use it, be happy to answer questions. So in our evaluation for the paper, we have selected 3 tools. So we have selected Astrea, which is a thread modular abstract interpreter. CBMC, which is representing here a SAT encoding of a symbolic POR. And Impara, which is a lifting of impact using interpolants with the DPOR. So here's a partial table of our experiments. The executive summary is that with over benchmarks taken from the SVComp and some parametric programs that we created, we have that Astrea is producing 6 times more false positives than us. CBMC is timing out over 50% of the benchmarks, and Impara is timing out even more, in 80% of the benchmarks. So the details of the evaluation are in the paper. So I want to conclude now. So we have presented a new approach to perform abstract interpretation in concurrent programs. This is using several techniques. Partial order reduction based on true semantic concurrency with using prime event structures. And as a design, we wanted to want to apply an off-the-shelf abstract interpreter for sequential code. So we have shown that the tool is being more precise than thread modular abstract interpreters, and it's more scalable than symbolic PORs. So for future work, we are now working on widening and abstraction for prime event structures. Thank you.
Thank you. Questions? Yes.
Yes, just a question about your prime event structures, which seem to be a compact representation of a number of executions. But maybe you can explain a bit how you represent them efficiently in your program.
How do I represent efficiently?
Yes, yes. I suppose an impression could be that these prime event structures representing many executions can grow very large because they represent many.
Okay.
So how do you deal possibly with this problem?
Right. So that's a very good question. So I just want to remark that events here are applications of fixed points. So an event here is really an application of an abstract interpreter. Now, typical construction of event structures are BFS. So they are keeping the entire event structure in memory. So what we have done is we have taken the work that we did for Concur 15, where we have a DFS exploration over the event structure, meaning that it will be as efficient as an optimal partial order reduction in that sense. That's a very interesting question. Thank you.
One more question.
This seems to be related to causality-based model checking. I think with the difference that you're looking at the unfolding rather than at a subset of the unfolding which consists of the necessary events to reach a violation of a property.
Right.
So my question is, have you looked at filtering the unfolding?
Yeah, right. So property-guided, right. So I guess your question is more about how do we do property-guided exploration of the unfolding in some sense.
Specifically, causality-based model checking, which does that, right? It
Right,
starts from
right.
the property.
Yeah, well, I think there's been some work that published in Concur, I think 12, on how to do a property-driven exploration of partial orders in some sense. We have some results. It's something we could talk about. It will be interesting to see what you think.
Okay, thanks.
Okay, thank you.
Yeah, thank you.
Thanks.